Hello. In this video, we're starting to wrap up our chapter on bonding in molecules, and we're going to look at some of the properties of those bonds, specifically looking at covalent bonds. I'll have a follow-up video. We talked about this a little bit in class, but also thinking about ionic bonds and how do we understand the strengths of ionic bonds as well. But let's start with covalent bonds. So we have different kinds of covalent bonds, and the main differentiation we make is between whether a bond is a single bond, a double bond, or a triple bond. And in theory, you can go higher than that, but we'll limit ourselves up to triple bonds, and that's the highest you'll see, generally speaking. And we've already kind of looked at this a little bit when we were talking about resonance. So, for example, a single bond would be something like something between, fluorine. If we look at a Lewis structure for fluorine, we get this structure here for F2 gas. And there are just two electrons that are shared, and so that's what we call a single bond. For oxygen, we get a double bond. And then for nitrogen, we get a triple bond. And you can go through and double check these Lewis structures, but these are the correct Lewis structures for these molecules. And in general, when we think about bonding, we're going to see trends related to these. So in general, if we're talking about the lengths of bonds, if our shortest bonds will be our bonds with the most electrons shared between molecules. So triple bonds tend to be our shortest bonds, and then the next shortest is double bonds, and then our longest bonds are going to be single bonds. And so this is a trend that we can observe. In particular, you can observe this if you're looking at the same molecules bonding. For example, looking at single bonds of two fluorines versus double bonds, two fluorines. So fluorines don't generally make double bonds. Anyway, let's go ahead and look at some actual data that supports this. And this is the data that helps us support, for example, in something like ozone, where we get this resonance structure where we get sort of a shared, this is the proximate structure of ozone, where we get this shared electron pair between both of them, where this is about between a single and a double bond. In terms of the bond length, this is the evidence that supports the fact that this is what's actually happening. So let's look at some actual data here. This is a table from your textbook. And let's highlight just looking at, for example, carbon here. So carbon-carbon single bond versus double bond versus triple bond. And we see a very clear trend in the bond length here. So bond length measured in picometers, that it's largest from a single bond and then decreases as we go down to a triple bond. So a very clear trend there in terms of the lengths of how long these bonds are. We can see the same thing for carbon-nitrogen bonds in our next set of three here. So we go from a single bond to a triple bond. Now these bond lengths that we're looking at here, these are averaged, so the exact bond lengths depend on the specifics of the molecule, but this gives us an approximate idea. If you take a bunch of molecules that have carbon-carbon single bonds, what's the average bond length if you look at several of these and average it over many different molecules? And so when we're looking at the same kind of bond, whether that's carbon-carbon, carbon-nitrogen, or in the next set of three, the carbon-oxygen bonds, we see the same trend for all of them. Now, if you're comparing across different kinds of molecules, you may not get exactly the same thing. For example, our nitrogen-oxygen, triple bond here is quite a bit shorter, or our oxygen-hydrogen single bond, even though it's a single bond, it's even shorter than this other triple bond. So you also have to consider which specific atoms are involved and how big are those atoms. The fact that hydrogen is really small means it can get a lot closer to the oxygen, even though it's only a single bond. So these trends we're talking about are relative to two of the same atoms bonded together when we're looking at trends in terms of the length. Now, the other thing we can look at is the bond strength, or the bond energy. And this is how much energy does it take to break the bond. So this is amount of energy required to break the bond. And we measure this in kilojoules per mole. And so what we're thinking about is if we had a mole of these bonds or a mole of molecules that had these bonds in them, how much energy how many kilojoules would we need to put in to break a mole of these atoms apart? So for example, if we're looking at something like nitrogen here, this is the energy, if we add energy into this to break this bond apart and form just two nitrogen atoms by themselves that are not bonded anymore, right? So they would have these Lewis symbols. Just making sure I counted up right. Yeah, five electrons around nitrogen. This is what we're talking about. So, and this has the trend where a triple bond has the highest bond strength, so it takes the most energy to break apart, so largest bond energy. So the strongest bonds, it's much more difficult to pull them apart because there are more electrons holding those atoms together. And then double bonds take a little bit less energy, and then single bonds less still. And it's honestly not just a little bit. Let's look at, again, some specifics here. So looking at our first set of carbon-carbon single bonds, we go from 348 kilojoules per mole, and it increases as we go down to requiring more energy. Oh, that makes me realize that I drew these backwards. This is the highest, this is the smallest. There we go. Now greater than signs are the correct way. But it takes more energy, much more energy, in fact, more than double the energy to break a carbon-carbon triple bond, this 839 kilojoules per mole, versus a carbon-carbon single bond. Again, you're going to want to compare these across similar kinds of atoms, but just gives you some idea. So when we're talking about, and we can see the same trend here for nitrogen, jumping down here to this part of the table here, as we go from a nitrogen-nitrogen single bond, which only has a bond energy of 163 kilojoules per mole, we can go to a nitrogen triple bond. It's a very strong bond. Requires 941 kilojoules per mole to break a mole of these bonds. Right, so those are the basic trends that we see in terms of how strong are bonds and how strongly are these atoms held together in molecules. In general, as you go from single to double to triple, the atoms are held more tightly together. It's more difficult to pull them apart. And when they're held more tightly together, they're going to be closer to each other, and so the bond lengths will get shorter. And so that gives us a way to think about relative bond lengths and bond strengths, just thinking about single versus double versus triple bonds. In the next video, we'll look at how can we use these bond energies to approximate enthalpies of reaction. And so we'll get there in the next video.